All right, thank you. All right. Hi, and welcome to the Geo-Institute web conference Launch and Learns. Today's Launch and Learn is being provided by our gold sponsor, Keller North America, and our presenter is Jim Gingery. Jim is the chief engineer at Keller North America, and he's going to be talking about deep soil mixing. Jim, the floor is yours. Thank you.
All right, great. Can you hear me okay?
Yes.
All right. Let me just get myself situated here. Okay. All right. Well, welcome everybody, and thanks for attending this Lunch and Learn. I hope you find it interesting. I'm going to talk about mitigating seismic extreme events with deep soil mixing today. Here's a little bit of an overview. I want to jump right into things rather than talking about them. So we got a lot of slides to cover, so I'm just going to keep going here. So first, an overview. You know, deep soil mixing is one of dozens of techniques that we have available here at Keller, and but it's a very popular technique for seismic mitigation, especially in the Western United States, and it is involving a high torque large drill rig that introduces a binder, which is typically primarily cement, Portland cement, could be slag or other additives too. It is mixed mechanically with the soil to create soilcrete with strengths that typically range on the order of 100 to 500 psi. And we can mix to depths of up to about 110 feet with rotary rigs. With cutter soil mixing, you can go even deeper. Typically with rotary rigs, you use columns that can be combined to form panels and grids and all kinds of different shapes for different applications. And when you whatever volume of grout that you introduce into the ground, basically that's going to generate an excess volume of spoils that needs to be disposed of. So that's one of the aspects to keep in mind when you're looking at soil mixing. So here's a typical layout at a site. We have the drill rig, which is doing the soil mixing. We have a pre-drill that's making a little cavity to catch some of the spoils. There's a batch plant over here that's got silos of dry cement, mixing it in an agitank to make the grout, and then it's pumped over to the rig and down the hollow stem and injected at the tip of the mixing tool. You have to have cement deliveries because we consume a fair amount of cement, so you need to have access for cement trucks to come through. You can have a loader or an excavator handling the spoils and so forth. And over here is a core drilling rig that's doing QA/QC coring, which I'll talk about, which is part of our quality program. And this is just another photograph of this typical setup for the batch plant and one of the mixing rigs with the completed soilcrete columns here in the foreground and the mixing rig in the background. So when you're mixing columns, you can configure them onto all kinds of different shapes. They could be what I like to call lattice grids, which are sort of interconnected panels that have a lot of shear resistance on lateral loading. You have isolated columns, which are good for vertical support of bearing loads, basically. And then you can make shear panels, which can be good for slope stability to reinforce slopes. And the mechanisms that are at play here with soilcrete and soil mixing is number one in solidification. So whatever ground that we're treating with the deep soil mixing is going to be turned into soilcrete. And it basically is like a soft rock. I'll show you some photographs later where we've made some cuts into soilcrete, and you know, it looks like a sort of soft rock, like a sandstone, siltstone material when you're done. The second is shear reinforcement. So when you make panels or lattice grids, and if you shake that horizontally with an earthquake or load it horizontally with a slope, then you will generate a lot of resistance in the form of shear stiffness and shear strength. And then finally, foundation load support For the vertical elements, or for vertical loads, we can take those loads and transmit them down into the ground, kind of like a pile does, down through a soft layer into a more competent bearing layer. So shear reinforcement is really important for liquefaction mitigation. And what it does is basically, since the soilcrete is on the order of 20 to 30 times stiffer than the soil that's in between it, when an earthquake ground motion propagates upward and shakes the system back and forth, the stiffer soilcrete attracts the load and takes the shear load off of the soil that's left in between the columns. And these curves here represent the kind of reduction that you get with ARR, the replacement ratio, the area of the soilcrete divided by the total area on the x-axis. And then GR is this ratio of the stiffness of the soilcrete to the soil. Typically, we're in this shaded range here. So we're talking about reducing the load on the soil, or you can think of it as a reduction in the peak ground acceleration. If you're doing a liquefaction triggering calculation, you're talking about reducing it on the order of like 80 to 90%. So that's quite a significant reduction of the load on the soil, and that can be enough to keep it from liquefying in the first place. And then even if there's still some liquefaction that might show up and occur in these layers, you still have if there's a foundation sitting on the system, it's still, the loads are going to be taken up by the soilcrete and transferred down to the competent layer. So even if you have a little bit of liquefaction and settlement of the soil within these cells, you still have the very significant bearing capacity support of the soilcrete itself. Quality assurance and quality control is really important. The primary tool that we use is the stack system, which is basically all of our rigs are instrumented with a number of sensors and recording quite a number of parameters. And we can, number one, measure the binder content, measure and control the binder content, which is the dry weight of cement divided by the total volume of soil mixing that's going into the ground. We have a target, which is this dashed black line, and the blue line is a derived from the measurements of where we're checking the grout SG and flow rate and the penetration rate, and it can compute the amount of dry cement binder that's actually going into the ground, which is represented by this blue line. The red line here is the blade rotation number, which is the number of circulations of each mixing blade over a 1 meter interval. So that means that over a 1 meter interval, we're circulating a blade through that thing 600 times. So that's a lot of mixing energy that's going into the ground. And depending on the soil type, clays and silts and require higher BRNs to get good mixing, good uniform homogeneous mixing, and sands require lower BRN. So this is another important parameter. The drilling index is sort of a measure of the drilling resistance in the form of the crowd pressure and torque and penetration and rotation speeds. It's computed from those parameters, and it can give you a sense for, if you're looking for a bearing layer, you can kind of think of it as analogous to a CPT penetration resistance. If you hit a hard bearing layer, you're going to see this thing sort of take off like that. It can provide confirmation if the design involves reaching and penetrating into a bearing layer. Then during the mixing, once the column is completed, we'll put this little trap door bucket, extend it down into the soil mix, and grab a sample out of it, cast it in cylinders and break those cylinders. And typically we're designing for a 28-day strength, so we'll break them at different dates, different curing dates over time, but the 28-day is the day that, the curing time that we are sort of using as our contract specification compliance measurement. We also do coring. We look for uniformity and core recovery and presence of clods and so forth. And we also can take samples from the coring and break those. So I'm going to cover a couple of applications here. First is a project in the San Francisco Bay, right along the bayfront. It's the renovation of a closed down power plant, and it's being developed. It's a large project that's being developed for multi-use applications. The waterfront, as you can see here, is a sort of industrial waterfront. It's being transformed into a beautiful public sort of area with a wharf and piers and so forth. But like everything around the San Francisco Bay, we have this Young Bay mud, which is a normally consolidated clay, fairly weak. It's prone to cyclic softening when you shake it back and forth with an earthquake. And overlying the Young Bay mud are old fills, which have layers of sand and pockets of sand that are have a low density and are liquefiable. And this site's only a few miles away from the San Andreas Fault, which is capable of generating a magnitude 8 earthquake. So there was an estimate of seismic slope displacements from the Bay mud and liquefaction ranging from 2 to 4 feet. And Keller's design and was Keller performed a construction and design to mitigate that lateral spreading displacement. So this is a little bit more detail on the soil conditions. Here's the Bay mud layer from 30 to 50 feet or so, and then about 30 feet of fill with pockets of it being liquefiable. So when we design buttresses to stabilize slopes, there's a good reference here, FHWA 2013. But FHWA is it's pretty much focused on static applications. So there's a little bit of discussion about seismic applications in Boulanger and Shao in 2021. And I'll have all these references listed at the end of the presentation in case you're interested in getting them. But we want to do checks of global stability, overturning and sliding, shear on vertical planes, and bearing capacity at the toe, and then extrusion between the panels. This is what the layout ended up looking like. We have these secant columns, overlapping columns forming panels. They're spaced at around 20 feet and they're going around, varied across the site, but they're going something on the order of like 70 to 80 feet deep. Typically, when you do these kinds of panels, you need a width to height ratio that's on the order of 0.7 or so. And the reason for that is that it's basically to resist the overturning. If you make it too slender, it's just going to overturn and won't have the shear resistance that it may have enough shear resistance for shear planes going through it, but you won't have enough resistance to overturning. So we adopted a sort of performance-based design for this project. The owner wanted a design with a relatively high level of analysis and designed according to performance-based sort of methodologies. And that means that we're designing for displacements and performance rather than factors of safety, because in seismic engineering, really a factor of safety can be kind of meaningless. A factor of safety of 1 might mean that there's 3 inches of displacement. Could be acceptable for a project. Or a factor of safety of 1.1 might mean that there's 12 inches or 2 feet of displacement. So we focused on displacement-based methods, and we used numerical modeling techniques using FLAC with nonlinear models to model the site. And this is one section of the site. We analyzed a couple different sections that's showing the discretization of the mesh and the layering in the model. The upper green and yellow is the sand fills, and then we have the Young Bay mud in the purplish color, some Old Bay clay, alluvium, and residual soils and bedrock underlying that. And the upper one is, first we run it without the DSM buttress, and then second we run it with the DSM buttress. And for the DSM buttress, we're using the composite stiffness and strength that you would get based on the area ratio of the soil mixing. So we use sophisticated constitutive models, including PM4 sand and PM4 silt. This is just one example of the many calibrations that we did with this PM4 silt model for the Young Bay mud. It's really important, obviously, to calibrate these models. They're very effective and can be very effective in making estimates of displacements, but they need to be properly calibrated in order to get reasonable results. So this is just one of those examples. And here are some of the results that we obtained. On the top here, this is for the case without the DSM buttress, and we got up to around 3 feet, around 2.5 feet or so at the crest. And comparing this with the conventional limit equilibrium with a Newmark type displacement, we got similar displacements with Brand-Macedo and the yield accelerations that we calculated. We got about 1.8 to 2.8 feet. But what you get out of the nonlinear deformation analysis, I think if it's done adequately, that you get a better representation of the distribution of the displacements across the site. So whereas this only provides you an estimate of displacements on a assumed slip plane. So and you're not always going to get the same value of displacement. I think this site was sort of unusually high in the agreement between the limit equilibrium and the NDA, but it gave us more confidence in the nonlinear model to see the more conventional analyses in good agreement. And then this is the analysis result with the DSM buttress in place. And again, this is just for one of our time histories. I think we ran 6 time histories or so and look at a range of results. You can see the DSM buttress is preventing displacements, significant displacements behind it. In front, you still have the some slope displacements because the DSM can't really do anything about what's in front of it on the slope. And so there's still a couple of feet of displacement on the slope and on the base side. Again, we got pretty good agreement with the conventional analyses and with Newmark predicting about 0.1 to 0.2 feet of displacement. But this, again, you get a better understanding of the distribution of displacements from the nonlinear model. And in some configurations, especially where like the DSM buttress is further away from the face of the slope, the equivalent linear, sorry, the conventional limit equilibrium analyses start to get a little bit more difficult to get reasonable results out of them. Okay, so here's some photographs from the site construction, working along the waterfront. This makes it look like we were right on the water, but we were really probably like 12 or 15 feet above the bay level. And here's a photo from basically inside the cab where the drill operator has a readout, and he's seeing all those same parameters that I showed you from the DAC report plus more in real time, so that he can control the work and make sure that we're achieving the parameters that we set. The rigs are all automated, and the pumping system and DAC system is all automated so that the pumping rate will automatically change in order to achieve our target binder content. So if there's a change or variation in the specific gravity of the grout, or if there's a slowdown or a speed up of the penetration rate, then the pump automatically adjusts to account for that, so that we get a consistent dosage. And that is a huge, huge benefit and a way to get nice, consistent mixing. So the next project is a pump station in Southern California, a new pump station. So you have this existing pipeline coming through, and the project consists of intercepting that with a junction box, tapping into it, running those pipes over to some wet wells, and then there's a structure above the wet wells, and those wet wells and their pumps will pump the material to other the water over to other parts of the plant. If we look at a cross section through here, through the wet wells, it looks something like this. The soils consist of the upper 15 or so feet of stiff clays and silts, and loose to medium dense sands. Where this material is below the groundwater table, it's liquefiable. And then it's underlain by medium dense to dense sands. Some of those the sands were a little bit liquefiable. And the wet wells extend down to about 36 feet below ground. This is what the structure kind of looks like. There's a concrete structure and a mat, and then these concrete wet wells going down into the ground. So the hazards at the site were there was liquefaction, yes, and a bit of settlement and liquefaction to deal with. But the biggest problem at the site was that there are active earthquake faults, secondary faults at this project location. And the site is so congested from with other existing facilities that this pump station simply could not be moved anywhere else. So the challenge here was to protect the pump station from earthquake fault rupture. And so with earthquake fault rupture, field experience has shown that, you know, big blocky kind of monolithic structures like a strong a concrete structure on a thick mat can be hit by a surface fault rupture and just, you know, ride it out or kind of surf it out. Other things like a telephone pole where it's monolithic, this fault trace went right through the pole, but the telephone pole was still standing and performed acceptably considering the circumstances. On the other hand, if you have something with a distributed foundation like tree roots, for instance, and one side of the fault is pulled and the other one direction and the other is pulled the other direction, then it grabs onto those roots and it's going to rip apart the structure like you see in this photograph from Turkey. So what we're shooting for is a monolithic behavior versus a distributed foundation behavior. And since we have those two wet wells, that was kind of like two big tree roots. And so we need to come up with a strategy that would counter that. And the strategy that we developed was to construct a deep soil mixing block to make it all big one monolithic structure. Excuse me. This was a fairly novel approach as far as we knew. This was the first time this kind of approach had been used. And so we wanted to make sure that it would work, and therefore did some very rigorous analyses and modeling to support the design. Here's the FLAC 3D model that we developed. This is the, I'll have a little cut through the middle of it showing the deep soil mixing block, which was 50 feet deep. It has the wet wells. We even put the structure of the building in. We found that in initial runs that we weren't able to get a reasonable response without including the structure, because the structure had a lot of stiffness and it interplayed with the response of the wet wells. And then we have the faults going through here, and so we use interface elements to represent the capability and the potential for slip on that fault plane, which has a reduced strength relative to the intact material. So here are the modeling stages. We build the site, let it come to equilibrium. We build the DSM block, and then we build the structure, and the faults are there. And then we impose the displacement across the fault on the bottom, and you can't see it over here, but on the sides of the fault. So it's kind of like you're holding the thing and making it move like this. And then you let the system solve and determine what the displacements are in other parts of the model. So the displacement that we put onto the model was 1.5 feet of horizontal, right lateral, left lateral rather, strike slip displacement, and 4.5 feet of vertical displacement. And these displacement values were determined through a pretty rigorous geologic investigation and a probabilistic fault displacement hazard analysis, which I don't have time to go into right now. So if you first run the model without the structure in place, you're going to see the slip is concentrated on the fault. As you would expect, usually the fault displacement is sort of like a knife edge sort of mode of displacement without any, as long as nothing's in the way. But if you put this big block of soilcrete in the way, what you see happens is that the slip comes up as a knife edge from the bottom. Excuse me. And then it hits the block and it doesn't shear through the block because the block is too strong. What happens is that it basically slips on the bottom, it distributes some of the slip across the soil here, and the whole block is acting more or less rigid and kind of rotates to accommodate the displacement. And there's some internal shear strain that's occurring within the block. You know, it's distorted a little bit, but what we did was we determined all the displacements from the nodes of the structure of the wet wells and the mat, and we took those displacements and we gave them to the structural engineer who had the same mesh, and they put them into their model, and they did a rigorous analysis of the response of the structures and found that the displacements that did occur were okay. This is what the layout looked like in plan. As you can see, it's 100% replacement ratio, so all of the columns are overlapping. It's all soilcrete everywhere. The average design strength on this was 500 psi, and we also tried to leave some lower strength material in these excavation zones that had to come out. Here's some photographs from the construction. And here's a photograph after we were done with the site and they were digging the wet wells, so you can kind of get a sense for what soilcrete looks like. Like I mentioned earlier, it looks like basically a sandstone siltstone. And these materials were, before, these were loose sands, loose sands and stiff clays, medium stiff clays. And you can see that they're able to make these excavations at nearly vertical even without any shoring at all. That's how strong the material is. Okay, the last one is a foundation support, kind of a more run-of-the-mill sort of typical application for soil mixing. This is at the San Diego airport. There was a couple of existing fuel storage tanks here, and they needed to add some additional aviation fuel storage tanks. So if we look at a cross-section through the site, there's about 10, 15 feet of sandy fill that's liquefiable, and then it's underlain by bay deposits which were interbedded soft to medium stiff clays and loose to medium dense sands that were liquefiable. So we had a problem of the bay deposits and the fill being compressible and liquefiable from a static standpoint, and then liquefiable in a seismic event. Underneath those, we had a dense bearing layer, fortunately about 45, 50 feet down of this old pyritic deposits. So we designed a deep soil mixing ground improvement zone to support the tanks on the mat foundation that came down through the soft materials and bared on the old pyritic deposits. So here's a CPT, just some of the liquefaction triggering results that we did. The red zones are liquefiable. You can see there's a few zones, shallow zones and deeper zones with liquefaction. There's about 2 inches of post-liquefaction seismic reconsolidation settlement. And if we run the shear reinforcement analysis at an area ratio of about 45%, it would reduce the PGA by about 90%. It makes the cyclic stress ratio go down from up here, way down here. Now the cyclic resistance is higher than the cyclic stress ratio, and the factor of safety goes way up, and the settlements have gone down. So this is how the liquefaction mitigation design worked on this project. So we calculate seismic and also the static settlements, and we look at the compression of the DSM zone and the soil beneath it. We check for bearing capacity. We check for edge stability, both seismically and statically. And this is what the layout looked like, a kind of wagon wheel layout to achieve the area replacement ratio. And here's some photographs and a little time-lapse video from construction where you can see how the soil mixing process goes. And there's the completed project with the new tanks, which you'll see if you ever fly into San Diego, look to the right and you'll see the tanks over there. It's a successful job. Okay, so here are the references, like I mentioned, available for you. And now we have a few minutes left for question and answer. Let's see, I will look in the chat to see if you have any questions. So there's one here. If lateral spreading movement occurs in front of the DSM buttress at the Patera Power Station site, how do you protect the exposed DSM face from erosion? Or is this condition only addressed after the earthquake? Also, how do you prevent, let me answer that question first. So I think if there was a major seismic event like this, like the maximum considered earthquake, the expectation is that there will be some repair work to be done, and there would need to be an evaluation of the post-earthquake condition. And I would expect probably just some riprap placement or something like that would be enough to do the repairs. Although we have on occasion used soilcrete, either by soil mixing or jet grouting as a erosion resistant kind of as a tool for erosion resistance, like in creek beds and stuff like that. How do you prevent impeding the flow of groundwater toward the bay and prevent the buildup of hydrostatic pressure? So that was on this project, we used those panels. The panels didn't have cross panels that connected them. So the groundwater is 80% of it, the ground is there for the water to flow through without being impeded. So, but that's something to keep in mind if you are designing soilcrete. If you design a grid in both directions, soilcrete has a very low permeability, and it will impede the flow of groundwater. So it's something to keep in mind if you're evaluating it. Let's see. Here's another one. How does verticality look in the DSM, and how to determine if there are gaps between DSM at depth due to deviation? So that's a good question. The rigs do have a inclinometer on the drill on the mast. So we do measure the inclination, and we're usually within like less than 1%. And that's typically sufficient to maintain the overlap. And if we're doing an application for soil mixing, like for groundwater cutoff, where we want to make sure that we get overlap everywhere, you might use a cutter soil mixing technique, which can you can get even better control of the verticality and just the shape of it, which it produces a rectangular shape and plan. Just the shape of it alone will help you to get the full overlap over the that you need for things like groundwater cutoff. We have some time for any other questions, if there are any. Make sure I didn't miss any. All right. Going once, going twice. If you have any projects where you think soil mixing or any other ground improvement technique might be applicable, or you have any questions about it, whether on feasibility, we're always here available to help out. You can contact me here at my email address, jamesgingery@keller-na.com. And yeah, happy to help you out, take a quick look at a site, and give you an idea of the feasibility for different ground improvement techniques.
Okay, thanks very much. We really appreciate your joining us for this Lunch and Learn and for this very interesting topic. We'd like to thank Keller for being the gold sponsor for our web conferences this week. Keller is also one of our organizational members. And if you'd like to learn how being an organizational member can benefit your company and support the mission of the Geo-Institute, especially for students, you can find more information on our website, and I will also post a link in the show notes. Please remember to like, share, and subscribe. We'll have some live streams coming up next week, so you'll want to put your reminders on for those. And thanks again for joining us. Have a great weekend.
All right, thanks everybody.
Thank you.
You're no longer streaming.